Hey everyone, in this video we're going to go over test 3, and I just wanted to point out mistakes that a lot of people made on it, so if it comes up on the final it's not an issue. And I wanted to go over kind of how that grade sheet I sent out, how that is set up. So looking at the first question, it says applying the superposition principle, which if you recall, the superposition principle is just saying that we could add two functions together to make a third function that is the sum of those two. So two functions could be represented as one, is basically what that idea is. Give a function that would add to the sum of the functions below is 0 everywhere. So we're looking for a function that would, if we added these two functions drawn on the graph, plus this third function would equal 0. So basically, if we could find a function for each of these sinusoidal waves on the graph, we just need to take the negative of it and we would have our third function. And it says, draw and label a graph with 1.5 cycles of your function. Hint, this function will look a little odd. Be careful to plot 1.5 cycles. The sum of these two functions might have a much larger period than either individual function. And there's actually no one that plotted this right on the test. So how I graded question 1, if we look at the grade sheet, is you can see there's two sections here. Each one of these columns is a worth 5 points. So this column D is for getting the correct function, and column E is for graphing it properly. And as you could see, no one got, someone got, all right, a couple of people got the function right, but no one got the graph completely correct. Some people were closer than others. So let's look at what I did. So as I have written here, you could see that this is just our test out of 55 points, but our function 3 that we're looking for is the negative of function 1 plus function 2. And so looking at this, what we saw in previous videos is when we're looking for a function of a sinusoidal wave, we're just looking for one, our coefficient in front of the trig function is going to be the amplitude. So if we look at these two functions on the graph, we have one function has a amplitude of 1.5 and it's starting at its amplitude, and the other function starting at 0, but we see that it has an amplitude of 1. So we're going to have one function that has a dependency of 1 meter, its amplitude is 1 meter, and the other function is 1.5. So I called function 1 our wave that has an amplitude of 1.5, and our function 2 that has an amplitude of 1. And then we need to pick a trig function to represent these waves. Well, I went with the easiest, I tried to make it the easiest answer for this problem without having some phase shift in it. At the end of this, I'll give all the, there are 5 total answers we could have had for this problem, but the one I'm going to talk about was the most straightforward because we don't have to worry about a phase shift. So if we look at this first wave, this blue wave, we're starting at our max amplitude when time is 0. So to me, that's obvious that it would be a cosine function. When we're 0, we're at our cosine, or our trig function becomes 1, and we're just at our amplitude, which most of you got. I think this red wave is what really screwed people up, because when we look at it, well, we're at 0 when our time is 0, but a sinusoidal wave would come up instead of going down initially. So what we needed to do was take the negative of that 1 meter and have a sine function. And then in here, inside of our trig function, what we saw is that when we have a time-dependent wave, it's just 2 pi over our period. So however long it takes to complete one cycle, and then we're multiplying by time. So if we look at our two waves, our blue wave has a period, it looks like it's at 2.1. And then because we're starting at our max amplitude, we're coming up and down, so one cycle would end here. And then if we look at our red curve, we're starting at 0, we're coming down, we're coming back up, and we're coming back down. And I actually, when I plotted this, I chose the period to be pi. A lot of people put 3.1, which was okay too. But that was actually supposed to be pi, just so we could cancel and our function would be a little cleaner. Excuse me. So what we see is our period for the function 1 is got the 2.1 seconds, and our function 2 is pi seconds. So once again, all we needed to do was take the negative of these, and we get this function written here. So like I said, this is where you see these letters. It's just showing which column represented the points for grading. I thought that would be the most efficient way to do it. And so when we did this, we could have had several answers instead, because we could really have picked to represent both of these as cosine functions or sine functions with a phase shift. And several of you did it right and just screwed up the negative sign here or there. So we could have had, our other options would have been our function 2, which was 1 meter, could have been sine of our angular frequency times time minus 1.5 meters cosine of pi. That's actually which I have written on the screen. But we could have also done the 1 meter sine of the same thing that we have, but instead of having a cosine function, we could have had a minus 1.5 meters sine of our angular frequency times time plus a phase shift of pi over 2. And then we could have also taken in fact, I'm not going to read all these just because it's going to be redundant. I will post this with the test. So if you want to see the other options, what would have worked out, just take a look. I'll attach the PDF in the class email. Okay, so where everyone screwed up on the graph is that this function, like I said, was a weird looking function in the hint. And so what we needed to do is kind of not look at how many times we cross our equilibrium point back and forth for a cycle, because we could see that it's acting a little different as it crosses back and forth. We get this amplitude, we come back down, it's a little smaller, it's a little smaller, a little smaller, and then we see that it gets big again. So if we look at this pattern, we're starting down here, and we could see that these two peaks are similar. So what one cycle would end up being is if we're starting here and we see that when we get to this point right at 6 seconds, that we start repeating our pattern again. So what we needed to do, since our cycle took 6 seconds, we needed to graph 9 seconds. And I went a little bit more than that just so I could end at our equilibrium position, just to make it easier to draw. But I think the closest someone got was about 8 seconds, but I tried to grade that fairly easy, even though a lot of people struggled with it. But hopefully that's clear what went wrong. And whenever you do this, I would just plug it in your graphing calculator and go through and just look at each critical point and plot it, and then at whatever time. So look at what the time is for this max amplitude and what the amplitude is. Look at what time it's crossing our equilibrium position, and so on and so forth. And that's all I did for that problem. So let's take a look at question number 2. So in an experiment performed on the International Space Station, that's supposed to say, I guess I forgot that word, a box is attached to a spring on the wall as seen in the figure below, where the weight of the box while still on the surface of Earth was measured to be 330 newtons. What would the value of the spring constant need to be for the period of oscillation if the period is 1 second to occur? And if the mass is initially released from rest at 0.163 meters from the spring's equilibrium position, what is the speed of the mass 35.3 seconds after being released? So let's take a look how everyone did on this one. So basically this first column F is going to be if you got the spring constant right, which as you can see a majority of people have got that correct. If I have an updated grade on here, just ignore that. I will be sending out the updated sheet. But anyways, this is the grade for the spring constant, and this is the grade for if you got the velocity right at 35.3 seconds. So I think a lot of people had problems with the part of the velocity, and I think a lot of it had to do more with calculation errors. It seemed like a lot of people were rounding, but let's just take a look at what we have. So I tried as I went through to write all of our known values and what we're looking for. So we had the weight of this mass on Earth is 330 newtons. We have an amplitude of oscillation of 0.163. We have a period we're working with of 1 second. And then we're looking for that velocity and our spring constant. So from our formula sheet, we see our angular frequency is equal to the square root of our spring constant over our mass. We don't know our spring constant, we don't know our mass, and we don't know angular frequency. So we're going to have to make some substitutions. So first, we could say that our angular frequency is 2 pi over our period, which we know our period is going to be that 1 second we're interested in. So when we substitute that into the equation, now we got rid of one unknown. And then our mass is equal to, well, it's just our weight. Our weight generally is mass times gravity. So if we divide our weight by gravity, we'll end up with our mass because that's what we need for this equation up here. So if we plug that in, now our only unknown is going to be our K value. We know what our weight was, we know what gravity is, and we know what our period is. So solving for K, we end up with this equation, and we could just plug in all of our known values, and we should have got a spring constant of something of 1,300, basically in that range. And then looking at our second part of the problem where we're being asked about what the velocity is at 35.3 seconds, we could set up an equation. I chose cosine. Once again, we could have chose sine with an offset, but we're being told that time equals 0, that we're at our amplitude, and that it's being released from rest. So this would be the easiest way to go about it. We know when time's 0, cosine's 1, and we are at our amplitude of 0.163 seconds. And so we needed to take the derivative because we're looking for velocity, not position with respect to time. So if we take the derivative of our position with respect to time, we'll end up with velocity. So this is the chain rule. We need to take the derivative of the inside and multiply it by the derivative of the outside. The derivative of the inside has this t dependency, so we just multiply what is essentially our angular frequency, 2 pi over our period. And then the derivative of cosine is negative sine. And I think a lot of people miss the negative sign when they took that derivative. And I think that was a big issue. So we now know all of our values. We have a representation of velocity with respect to time. All we need to do is plug in 35.3 seconds for wherever we have our time, which is just in the trig function, and then plug in all of our other known values. And so it should have came out to be negative 0.97 meters per second. And it seemed like a lot of people were rounding and calculating this value in here. But since pi is irrational, as soon as you do that and then plug it in, a trig function can change significantly, even if the number is just rounded a little bit inside. So whenever you're dealing with trig functions, I would never try rounding, plugging it in as you go. Just plug this all in at the end. And I think I tried looking at a few of you because I think you were in degree mode instead of radians. Just remember we're working in radians when we're dealing with any sort of circular motion or periodic motion in physics classes. Okay, so number 3. This is another one that almost everyone had made the same mistake. So while constructing a waterfall in a pond that's 0.45 meters deep, you're faced with the task of choosing an appropriately sized pump to sit at the bottom of the pond and lift the water at a height of 1.33 meters to a waterfall. What is the minimum pressure the pump must produce to lift the water? And so whenever we have these problems where it's the minimum, kind of like when we were working with forces, what was the minimum force to get a box moving? It's just that pressure basically that would be able to hold the water up is what we're looking for, even though it wouldn't necessarily be moving at that point. It's just kind of the easiest way to go about solving this, because we know that if it could lift any more than that it would be, the waterfall would be flowing. And then we're asked, what is the magnitude, or if the magnitude of the water's velocity is 2.72 meters per second, and the pipe carries the water has a diameter of 5.75 centimeters, what volume of water is flowing over the waterfall per hour? So once again, if we look at our grade sheet, our first column is calculating what the minimum pump pressure should be, and our second column was the volume of water that would be flowing over. And as you could see, a majority of people did good with the volume, but not so great with the pressure. And as I was saying, it was pretty much the same mistake that everyone was making. So let's look at this diagram. We're lifting this up a height of 1.33 meters, but the pump is submerged in 0.45 meters underwater. So if we think about this, let's say this pump isn't on, it's just open, we already have the water up 0.45 meters. So really we're only lifting with the pump the difference between 1.33 and 0.45. And a lot of people actually ended up adding that instead of subtracting it. So we knew our height of our water, we know the height total, and we want to know the pressure of the pump. And then for the second part, we're told a volume, a diameter, and we want to know the volume of our water flowing over a period of 1 hour. And then, of course, the density of water is 1,000 kilograms per meter cubed. So the pump pressure, we could have solved this a couple different ways. We could have used Bernoulli's equation, but once we plugged everything in, if we plugged it in appropriately, we would have seen that our pressure here where the water's coming up is just atmospheric pressure, right? But down here we have the atmospheric pressure and the change of height of water as well. And so our atmospheric pressure would have canceled out, and we would have just ended up with this equation where we have the change of height, where it's the total height minus the height of the water, because once again, we're not lifting that water up. It's already sitting in the pond, this height. So the pump doesn't have to be able to lift that. And then it's multiplied by rho g. And if I had written Bernoulli's equation out, we would have seen our velocities, because once again, we're assuming the minimum pressure, that our velocity would be the same on both sides, which in this case, we would be just assuming that it's 0. Okay, so we plugged all this in, and we ended up with a pressure of 8.6 times 10 to the 3 pascals. And so this next part where we determine the volume, like I said, most of you got this one right. We just need to multiply our velocity, because it's meters per second, times our area, because that gives us meter cubed over seconds. And then if we multiply by our change of time, we get rid of those seconds in the denominator from our velocity, and we end up with meters cubed, which would be volume. So we're asked about 1 hour, which our velocities in terms of seconds. So we need to change our 1 hour into seconds, which if we do our dimensional analysis, we have 60 minutes in 1 hour, cancel the hours. We have 60 seconds in 1 minute, cancel the minutes, and we're left with 3,600 seconds. Our area is just equal to pi r squared. We're not given the radius, we're given the diameter, so all we need to do is divide that by 2 and then square that whole thing, and we end up with a volume equation for our volume of our velocity times d over 2 squared pi times our multiplied by our time. So we know all these now, and we could just plug those in. A couple things I saw wrong with people that didn't get this one 100% right was, one, they didn't convert our centimeters to meters. They didn't move our decimal place over, so it was in terms of meters. We're looking for meters cubed. We could have changed this first term to centimeters per second and solved it for centimeters cubed, but generally in physics we deal with meters and not centimeters. It's more of a chemistry thing. Okay, so now we got question 4. This was probably the most successful question out of the test. Looking at question 4 on here, we could see most people that answered the question got it correct, and it just was the first column's the velocity approaching each other, the velocity, or not the velocity, the observed frequency of approaching, observed frequency passing, and observed frequency retreating. And if you only gave one answer, I kind of just guessed which one it was supposed to be, because I just assumed you knew which one and it was right. So looking at my work, we have the velocity of the two cars, the magnitude of velocity rather. We have the frequency that's being generated, and we want to know the frequency of observed. The subscript A, P, and R are for approaching, passing, and retreating. So first we're looking at the velocity approaching. Remember that we have the speed, our V in this equation is the speed of sound. That is temperature dependent. It's also dependent on what it's traveling through, but we're just going to assume that it's 343 meters per second. And then we have the velocity of car 2 in the numerator, so this would be the observer's velocity, and velocity of car 1 would be the velocity of the source. And so we need to be careful. We want this, the number in the numerator, to make our value greater, because we know that as the cars are coming at each other, the distance traveled by the waves is less and less, so we know that our frequency should be increasing. And then the denominator should do the same thing, so we're going to add and subtract, because that will give us the an increase in frequency. And we see that our frequency approaching is 2.23 kilohertz. And so our velocity passing, well, our velocity passing, turns out our velocity 2 and our velocity 1 are going to be the same value, because it's the velocity that's perpendicular, or our velocity is not it. So basically our velocity that we're talking about is the velocity that's parallel to the sound wave direction. And so when we're passing each other, our velocity is perpendicular to the sound wave. So it's actually going to have velocity 1 and 2 is going to be 0, which would mean we just get our velocity of the speed of sound over the velocity of speed of sound, which of course is just 1, and 1 times our original frequency shows us that we have our same frequency that is actually being produced. So we don't see a shift in frequency. The observed and the source frequency are the same. And now for the retreating, it's just the opposite of our approaching, where we want the numerator now to make our frequency a smaller value, so we're going to subtract, and the opposite in the denominator, and we end up plugging it all in for a frequency observed of 1.98 kilohertz for the retreating vehicles. And so question 5, what would the gauge pressure read on the dive bell if brought to a depth of 100 meters in the ocean? So we're told that the density of ocean water is 1,023 kilograms per meter cubed. And so let's look at the grade real quick. So most people got this problem. This is probably by far the easiest problem on the exam. And it's similar to the waterfall problem, where we're just concerned about how the change in pressure. Once again, we could set up Bernoulli's equation, but we don't have velocity. Our atmospheric pressures are going to cancel because we're talking about gauge pressure. And so we end up with just rho GH, which I believe is also on our formula sheet for static fluids. The change in pressures only got to do with the change in height. And so we know our density, we know gravity, and we know our height. So it was as easy as just multiplying those three things together, which came out to be with sig figs 1 times 10 to the 6 pascals. And so number 6, a thin circular sheet of metal has a mass of 10 kilograms and a radius of length r equals 2 meters. Use the parallel axis theorem to calculate the moment of inertia of the sheet if the axis of rotation is moved 1.5 meters from center. So I was surprised actually how many people got this right, but now that I read it and I realize that I actually said parallel axis theorem in the question, that probably helped people pick out which equation to use. But yeah, we had a lot of successful guesses. If you guys lost a half a point on a question, it was because you either didn't put units or maybe you... I'm trying to think. I graded them yesterday. Maybe there was supposed to be a negative out front or something, and I don't remember. So looking at our answer, the parallel axis theorem tells us, well, first I listed our knowns. We know the mass of the disk. We know the radius. We know where our point that we're going to be rotating around is 1.5 meters from the center of this disk. And we're looking for the moment of inertia at that point P. So that's what this subscript P means. And so the parallel axis theorem tells us that if we have the moment of inertia at the center of mass and we add our mass of the object multiplied by our radius at, I'm not sure why I changed this to an A here, this should be a P, but at some point P squared will have the moment of inertia at that point. And I think the biggest mistake was people choosing the wrong moment of inertia for a center of mass. A lot of people just used mr squared, which would have been for a hoop, but this is a disk, as we can see in the illustration, that this is a disk that's rotating, which if you look at your formula sheet, we get I believe they call it the solid cylinder on it, and we get a moment of inertia at the center of mass of 1/2 mr squared. So we just plug that in. This r from center of mass is the radius of the disk, the total radius of the disk, and this r sub a, which should be r sub p, is that 1.5 meters. So now we know everything. All I did was simplify by pulling our mass out in front so I wouldn't have to plug it in my calculator twice. And we end up with this relationship, which gives us a moment of inertia of 42.5 kilograms meters squared. So hopefully if you had struggled with any of these concepts, this video helps. If not, if you still have any other questions, let me know. Like I said, I'll update the grades shortly and send them out.